Today we're going to be looking at hydrocarbons, and I wanted to provide a periodic table just to share with you what a hydrocarbon is, and we'll get to the definition of hydrocarbon. This is an actual test question. I believe it's even a homework question. It asks, what's the composition of a hydrocarbon? And I've highlighted them right here. Hydrocarbons contain hydrogen and carbon. Sometimes people can get confused because they think hydro in terms of like hydroelectric, which means water. But in this case, the hydro really is just referring to hydrogen, and the carbon is referring to the carbon. So let's go ahead and get started. We're going to start with our emphasis on carbon. So just to go back to the periodic table, if you look at carbon element number is 6. So carbon is atomic number 6. So what that means is that it has a total of 6 protons and also has 6 electrons. We're going to be more concerned with the electrons because, again, that's what determines its bonding. If we take a look at the shells, what we see is in the first shell, if you remember from the 2-8-8 rule, we can fit 2 electrons in the first shell, and we'll have then the remainder. Well, we already used 2 of our 6, so now we have 4 electrons that are going to be in the second shell. So here's the first, that's complete. Here is the second, that's incomplete. So carbon would be drawn like this, with 4 electrons. If you remember, they don't pair up until we fill up the 4 corners of the universe, north, south, east, and west. So carbon would look like this, which means that it's able to form 4 bonds. So carbon has the capacity to form 4 bonds. If you remember, we did a structure that looked like this. And the black represents the carbon, and the whites are going to be representing the hydrogens. So each of these stick figures is going to be the bond, of course, and so carbon is able to form 4 bonds. So it's an important thing to note that carbon will always form 4 bonds. So let's take a look at hydrocarbons. Again, the name hydrocarbon. Hydro is not referring to hydro as in water, like to hydrate yourself. Hydro is actually referring to hydrogen. So hydrocarbons contain hydrogens, and they contain carbons. That's their composition. The main function of hydrocarbons is found within their structure. I'm going to draw a little hydrocarbon here, and we're going to draw maybe just a 2 carbon structure here. And if you can put all their bonds around. So carbon, remember, has the ability to form 4 bonds. So we have 1, 2, 3, 4. This carbon has 1, 2, 3, 4 bonds as well. Let's go ahead and surround these right here. And a lot of the energy is within these carbon-carbon bonds. But if you take this hydrocarbon, and if we react this with some oxygen, this will be a combustion reaction, and we get a rearranging. The carbons interact with the oxygens to form carbon dioxide, and the hydrogens also react with the oxygens to form water. Plus, we get lots of energy. We're burning this hydrocarbon, and it produces energy. And the energy is stored within the carbon-carbon bonds. There's also energy within the carbon-hydrogen bonds. And I want to have an analogy for you, and this energy is stored, and it's ready to be released. It's sort of like a glow stick. So if you can remember that these bonds within these hydrocarbons are like glow sticks. How do you get the glow stick to release its energy and release its light? You snap it. Just like these bonds right here. We're going to be breaking these bonds, and we have a large structure, and we're breaking them down into smaller structures. and that's going to be releasing a lot of energy. If you remember a previous chapter, we talked about larger structures with more organization. These are less organized and smaller. So these have more energy, these have less energy, and it's increased the entropy as well. It's increased the chaos. So we have lots of order and structure here, but we also have lots of energy stored in there. So let's take a look at some of the functions of here related to this concept of stored energy within these carbon-carbon and carbon-hydrogen bonds. Fossil fuels, this is a fossil fuel right here. It's called ethane. We'll get to the naming of them in a few minutes. But fossil fuels such as gasoline, and we'll get to the name of the hydrocarbon that's found in your gasoline, a common fossil fuel that some people might have to heat their homes. One of them is going to be propane, giant propane tanks. Or we can also have methane, for example. Gasoline, propane, methane. So what do these things do? Well, you put gasoline in your car and it combusts. We burn it. And it produces energy. It also produces heat from the flame that's being produced when we combine the fuel with oxygen in a small spark. And a lot of times this will enable the vehicle to move. We talked about in the prior chapter how the gasoline comes into the cylinder. The cylinder has some oxygen. We provide a spark from the spark plug. That then causes the energy to be released and the heat to be released. We get this expansion of gases that pushes the piston down, and it moves the piston, and that's connected to all sorts of things inside your car. So one of the functions of hydrocarbons is we can use them for our machinery. Hydrocarbons are also found in food, though, and that's going to be in the form of either fats or oils. If you remember, we made soap out of this giant molecule, and that giant molecule is called a triglyceride. And these triglycerides can be broken down into smaller pieces. Lots of carbon-carbon bonds that can be snapped and broken, and then that will release energy within your cellular machinery. So here with fossil fuels, we're going to be combusting them. We're going to be burning them. With food, we also burn our food, but it's not called combustion, it's called respiration. You probably recognize this from biology. And it's the same thing. We can use respiration because we need energy to power our cells, for functioning for our bodies. We need respiration to heat our bodies, to make our molecules optimal at the proper temperature, but also they enable us to move. Muscle movement, energy to provide neuron transmission of signals. So these are the function of hydrocarbons. We have carbon-carbon and carbon-hydrogen bonds, and there's lots of energy that's stored in between those bonds that are like glow sticks. And if it's a fossil fuel, we could then burn or combust them to produce energy, heat, and movement. Or if it's food, such as a fat or an oil, then we can also burn that, and it will also release energy, heat, or allow movement. So let's take a look at the different types of alkanes that we have. Okay, so what we're looking at today is we're looking at linear alkanes. And linear alkanes are these straight chains. So linear means that we're going to have these straight chained types of molecules, and as opposed to branched, which we'll see in the days to come. And it also ends in ane, an alkane, ane. These are going to be hydrocarbons that have single bonds only. So we have straight-chained hydrocarbons with single bonds. That's what linear alkanes means. We'll fill in this chart after we fill in this chart down below here, but I want to draw some of these for you. The first one is going to be this right here, and it's methane. It's a 1 carbon. We can see it has 1 carbon. The structural model, this is the 3D model. Okay, so I want to go back to the structural model. This is the 2-dimensional drawing, and it would look like this. The central carbon, and it has its 4 bonds. In order to save time, we're not going to draw on the hydrogens, and I'm going to be using this format. So whenever we have a bond like this, we're going to be assuming that it goes to a hydrogen at the ends. So the formula for this is going to be C, because we have 1 carbon, and we have 1, 2, 3, 4 hydrogens. So it's CH4. Okay, the name for this is going to be methane. And the example for methane, this is natural gas. This is the natural gas that comes through our pipes for our Bunsen burners. It might come into your house to be burned for your stove or to heat your house. If you're next to the city, you probably have natural gas because you're very close to the gas lines. If you're out in the country, you're far away from the main gas lines. It'd be very costly to get the methane to you. So people opt to have propane because it's more cost effective because they're too far away from those gas lines. So 2 carbons. So we're going from a 1 carbon to a 2 carbon. So if you can draw 2 carbons in here. So let's draw 2 carbons. And if you remember, we have to connect these now with the bonds. So each carbon is going to have 4. Let's go ahead and connect 1 between them right there. That accounts for one of the bonds for each of those carbons. So this carbon has 1, so now it's going to have 1, 2, 3. This carbon has 1 bond, so it can have 1, 2, 3 more. So now the formula for this is going to be C2 because we have 2 carbons. And how many hydrogens do we have? Go ahead and quickly count them. The formula for this is going to be C2H6. And this is going to be called ethane. Notice that they all end in ane, because we're looking at what are called alkanes. These are all going to end in ane. All of them actually will end in ane because these are all alkanes. So it's ethane, and there's no common example of ethane or common name for ethane as well. Next one is going to be a 3 carbon. So if you can put 3 carbons in here, 1, 2, 3. Can you fill in all of the bonds? Each carbon needs 4. This central carbon, it has 2 of its bonds already accounted for because it's attached to the other carbons. So it only is able to attach, I'm not going to draw the hydrogens. It's only able to attach to 2 hydrogens, while the ones on the end are able to attach to 3. So if you count these, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have C3H8. The name for this is going to be propane, like your propane tanks. So examples of where you would use propane is going to be maybe a barbecue. Okay, some homes also use this for heating as well. Or if you have a small propane tank like this, you can get flame coming out of that. So we got the propane tank going right here. I don't know if you can see the flame or not. I don't want to burn anything, so I'm just going to turn this back down again. Okay. So that is propane, C3H8. Going on to the next carbon molecule, we have 4 carbons. So if you can draw 4 carbons, 1, 2, 3, 4. Now follow this pattern. C, C2, C3. The next should be C4. Follow the pattern for the hydrogens. We have 4, 6, 8. It should be H10. Hopefully you got that. Now let's go ahead and count the number of carbons we will have. 1, 2, 3, 4, 5, 6, 7, 8, 9, and indeed we have 10 carbons. Name for this is going to be butane. And these are found in lighters. Can you see that? I don't know if you can see that. Oh, there we go. Thank you, lights, for allowing us to see that. So, butane. Butane is going to be found in lighters. Now, it's going to be very important to remember these first 4 carbons. And the first carbon starts with M, the next one starts with an E, the next one starts with a P, the next one starts with a B. And this is a common tool for you guys to remember large pieces of information when you're doing your lectures and studying in college, is to create these what are the anagrams? Oh, I can't remember the name of them. Where you try to create, like scuba is self-contained underwater breathing apparatus. So you try to create some type of word with these. And I always in college went MEP-B, and that's how I remembered the first 4, because I couldn't remember the order, so I created a name for it. One student a couple years ago said, why don't you just have it as MEPB? So if you can remember MEPB stands for the first 4 carbon compounds: methane, ethane, propane, butane. Let's take a look at these. We have a 1 carbon, 2 carbon, 3 carbon, 4 carbon, and we're going to go all the way up to 20, even up to 1,000 carbons. So these carbon compounds are very, very small. So the size of them is small. What's their mass compared to the rest of these with more carbons and more hydrogens? The mass of these guys are going to be very light. And because their masses are very light, they're not very dense. And because they're not very dense, their phases of being either solid, liquid, or gas is going to be a gas. Methane is a gas, ethane is a gas, propane is a gas, and butane is a gas. These are all gases. However, we start to increase the molecular size of these things, and what happens is they become more and more larger, they become more and more dense, so their phase is going to change from a gas to a liquid. When you get to a 5 carbon compound, you're actually going to be denser than air. So this compound name of 5 carbon, now we're going to be looking at the prefixes that you're probably familiar with. 5, 6, 7, 8. So the building that has 5 sides, this is going to be a pentagon, and so therefore this is going to be a pentagon that ends in A and E, just like the others end in A and E. So this is going to be called pentane. Okay, what is 6? 6-sided figure is going to be called a hexagon, so this is going to be called hexane. Now 7 is not sept. Remember from the prefixes earlier, it's going to be hept. So we have heptane. And 8 is oct, octagon, like a stop sign, and so this is going to be called octane. And octane might sound familiar to you because octane is the gasoline that you put into your car. When you're paying for 89 versus 93, this is the octane level or octane percentage. You have 89% octane versus 93% octane. So the more purified that it is, the more expensive that's going to be. So a higher percentage of octane is going to be more expensive. But octane is your gasoline. And this goes all the way up to a 19 carbon. These are all going to be liquids. Once we hit 20 carbons, we're going to be getting into something that is solid. So these molecules continuously become larger and larger and larger. Now they're in the liquid phase. They become so large that they don't have the ability to actually rotate or dance or roll around each other. They're so big that they're going to get stuck. And since they get stuck, that's going to create a solid. So the mass of these guys compared to these guys over here, they have more carbons, they have more hydrogens, therefore they're going to be heavier. Their size, because they have more carbons and more hydrogens, these are going to be larger. And of course, they're going to be liquids. So following the pattern, we're going to have gases, liquids, and we're going to have solids. The size of these guys, these are going to be the largest ones. And of course, their mass, because they have more carbons and more hydrogens, these are going to be the heaviest. So this ranges from 20 carbons up to 1,000 plus carbons. If you have 20 carbons, you have this material which is called parafilm wax. And it's this substance right here. We'll get to this. It's this see-through stuff. It's interesting, you can actually see through it because it's only a couple molecules thick. So we'll get back to that in a minute. So this is going to be our parafilm. And getting up to thousands of carbons, this is getting to your waxes, such as your wax inside your candle. So this candle wax is very, very hard. Okay, I can put my impressions in it with my fingernail, but I probably can't shape it. It's not, molecules aren't short enough. Again, the larger that they get, they become like logs, stacked logs that no longer have the ability to move around one another. Let's go back to the parafilm because the parafilm is a really interesting substance. This is 20 carbons. It is a solid, but it also has the ability to be stretched. This is used a lot for in biotechnology and culturing of bacteria within Petri plates. And what they do is they take this material and they stretch it out like this. So it's very, very, very stretchy. Okay, so this has now been mostly stretched out, as you can see. But what I want to do is I want to focus on what's going to happen is if I continue to stretch it more and more, it gets weaker and weaker and weaker, and eventually it's going to break. I want to show you what's happening because, again, these molecules are so large. I want to represent these instead of like this. I'm going to represent them as these long sticks. So here is a 20 carbon chain. Here's a 20 carbon chain as well. So these are all 20 carbon chains. And they're sort of lined up like this. They're just a couple molecules thick. And they line up and they're created like this. And when I start to pull apart and pull apart, these molecules will begin to slide away from one another. So what happens is it might end up looking something like this. Here's your 20 carbon, and there's this 20 carbon here. There's that 20 carbon. And these molecules, they slide past each other, and eventually, between here and here, they finally can't hold on to each other anymore, and what happens is it begins to tear or rip, or then it breaks. That is it for the intro to hydrocarbons.